Yeah, we've already covered chapter 1. Chapter 2, I think I've covered everything in chapter 2. This is all additional matrix functions, that they're array addition, subtraction, that they're, I just want to make sure that we don't miss anything that they're, array multiplication is basically, again, you're going to, as we do array multiplication, it's going to be a row times a column, the next row times a column. So when you do normal array multiplication, where's my pen here? Here it is. Hopefully my battery is up there. When I do normal array multiplication, I'm just going to show two by 2s right there. A11, A12, A21, A22, B11, B12, B21, B22. I'm going to get right here, when I multiply the two of these, this is this row times this column. So this is A11 times B11 plus A12 times B21 right there. This one here is the second column times the first row. A12 times B12 plus A22, excuse me, now I'm drawing that there. Actually, no, it's, yeah. This should be this should be A12 plus, okay, now I know this class is about ready to come to an end because it's this row, this spot right here should be this row, or this row times this column right there. So it should be A11 B12 plus A12 times B22. Yep. And up there again, and Dr. Wong saw me taking some for an upcoming migraine just before I came up here, so I am not joking. It's starting to shut down. So that's one of the problems with migraines out there. But again, we take this row times this column, then this row times this column to get this spot here. And what I'm going to do to make life a little bit simpler, right there, this row times this column gives me this spot. This row times this column gives me this spot. This row times this column gives me this spot. This row times this column gives me that spot. So that there, and if we have the situation of a 2 by 2, and I'm just going to say A, B, C, D times X and Y, it's going to be AX plus AY for the first spot right there, and CX plus BY for the second spot right there. Right there. I take right there. So you multiply arrays right there. Right there. And dividing arrays is a little trickier. I'm not going to talk about dividing arrays right there. The only other thing on arrays to mention is that we have special arrays. And one array that's special is the identity array that there, and that's the only one I really worry about. And that's one that's got ones on all the main diagonals. Everything else is 0 right there. And the identity array multiplied by any other array is going to give you back the original array. So if I have an array A, there may be an A minus. the inverse of array, that array. Not every array has an inverse right there. But A times A inverse is equal to I right there. Now, some people will put an IN right there to say whether it's a 3 by 3 or 4 by 4 or 5 by 5 right there. So if we could do matrix algebra, and I've already done a little bit with that there. Ohm's law said that V is equal to R times I, right there, right? Right there. Well, we had R times I equals V in matrix form, so we multiplied R minus 1 times R minus R equals R minus 1 times V. These two, that there times I forgot the I there. Those two drop out, and we're left with I is equal to R minus 1 times V, and that's how I solve my system of equations earlier, that there. So, that there. That's really all I'm going to get into on array multiplications and divisions right there. So, we don't necessarily divide by an array, we multiply by its inverse right there. We can't do a I is equal to V over R like that there. That doesn't work. That there. He does that R right B, and that seems to work, but I just prefer to use the R to the minus 1 notation that there. So again, I'm not going to, we're running short on time. He goes through this array multiplication. These, you've got copies of the slides. I completely botched up showing how to multiply two numbers together. But as you can see here, it's 6 times 9, and then minus 2 times minus 5. You can see that he's taken this row times this column to come up with this number right there. You know, right there. Then he's taken this row times this column to come up with this number here. So it's the first row times the first column fills in. So what we end up with is the number of columns here is going to determine the number of columns in the final answer. The number of rows in the first one determines the number of rows in the final answer. So this is a 3 by 2, and this is a 2 by 2. This determines the number of rows, and this will determine the number of columns right there in the final answer. Right there. So does that make sense in looking at what the final answer is going to be right there? So again, that's array multiplication right there. Again, you just use the multiply symbol without the dot right there. To multiply two arrays right there. Matrix does not have commutative in general. You cannot just flip those two around right there. So it's just one of those things. And again, this is not a linear algebra course, so I'm just going to skip through some of these discussions right here. Special matrices, I already talked about the one that I consider right there, and that's the inverse matrix right there, or the identity matrix right there. Right there. Type in zeros right there. There again, polynomials that there again, we have a function called convolute, which produces the product of two polynomials, and the result is a polynomial array. So if I have a function, and I'm just going to write this 3x squared plus 2x plus 5, so remember 3, 2, 5, times x squared plus 2 right there. So that's going to give me the arrays, and I'm going to write that down on a piece of paper so that I thought I had a piece of paper. I guess I'll use this here, right there. So my first array is going to be 3, 2, 1, or 5, 3, 2, 5. My second array is going to be 1, 0, 2, okay? And if I put those in, and here we go. Right there, I'm going to come back to that. This right here, I'm going to close it. I'll talk about that next. Up there. So we're going to say that A is equal to bracket, and we said that was 3, 2, 5, right there. B was equal to 102, right there. And we say C is equal to convolute. And make sure I spell that right. C-O-B, C-O-N-B, yep. A comma B, right there. And that gives me that my final expression should be, right there, I'm just going to put it here. My final expression should be my polynomial is going to be 3x squared plus, actually 3x to the fourth, 2x to the cubed plus 11x squared plus 4x plus 10, right there. So that tells me what my, so it multiplies my two polynomials out there. So again, we can do polynomial multiplication very easily out there. And you can sit down and look at that original polynomial and multiply the two. But if you just start off with the first one was it was 3x squared plus 2x plus 5 multiplied times, and I had 102, so x squared plus 2 right there. You're going to end up with, it looks like 3x to the fourth there, right there, plus 6x squared right there, plus 2x to the third right there, and that's what I had there, plus 6x squared right there. So my x squared there, or excuse me, that's, yeah, 3, no, that's not right. I'm botching this one up. I started it long enough to know that we got the right answer. Now I'm going to get the wrong answer and doing it by hand out there, and I'm just going to move on. If you go through and did that by hand, you would get what I had up here. I trust MatLab better than I do my brain right now. Yeah, there. This is a problem that there, and some of my students have a hard time actually when I say that. But once in a while, we're all human, and I know with a headache coming on that there's some things not firing up right there. So, but again, what you're seeing with the polynomial function there. And right there with the polynomial, and then we've got there computes the result of dividing two polynomials. This one's a little trickier, is that if I take my final polynomial and I divide the two, it will go through and divide the two and give me who's there by a polynomial that there, and will give you the the result along with the remainder right there. So it will actually divide two polynomials and give you that there. To be honest, I have never used it for that purpose. I think it's useful if you're trying to factor out, but again, you've got the roots function, and we've already talked about the roots function that there. Okay, that there, and here they give you quote and remainder that there, convoluted product, and here they've got an example. Again, I'm trying to rush through here a little bit. The roots we've already talked about, the coefficients right there. So here what we're giving here is, this is kind of an interesting one. Function computes the coefficients of polynomials. So we're telling it the roots, and it's giving us back the polynomial. So, this is actually, for anyone that spends a lot of time with polynomials, and again, in feedback control systems we do, the polynomial functions are almost as important to us in that particular area as the matrix functions are for a lot of other areas. But anytime you've got polynomials, this is really good for finding roots, finding polynomials, dividing polynomials. It does all those things that they're plotting polynomials. Again, we can do plots right there. Right there. And again, what we're looking at here, this is kind of an interesting thing here, is here's a function here called polyval. Right here. And this particular function is one that I really like. And it's one I really wasn't going to get into, but when I was reviewing before the break, I looked at this as I really got to cover this function right there. And what we do is we define our polynomial right here. And we define our polynomial by filling in this array right here, right there. So 9, -5, 3, 7. Then we define our values of x, the range in which we want to plot it. And then we say f is equal to this. And then we use the plot xf right there. So f polynomial actually creates a new array called f that evaluates this polynomial. We don't have to write a function for writing this polynomial right there. So I'll give you an example right there, and I'm just going to pick a random polynomial. I'm going to pick 3x squared plus 2x plus 5 or something like that. And I'm going to plot it from -10 to +10 right there. Again, I don't know right there. But again, what we're going to do is we're going to say that a is equal to, what did I say, 5x squared, 3x, 11, no, right there. So there's our polynomial. We're going to say x is equal to, right there, bracket, and we're going to say -5. Now there, I'm just going to use equal linspace. -5 plus 5, 200 points. Right there. Right there. So now we're going to say f is equal to polyval a comma b. Right there. And, we did x. This is x. Right there. And now we can just do plot. And again, we're going to do x and f right there. And there's our polynomial right there. Our plot between -5 and 5. So we can give it any polynomial, and that there. And I can go through and change a. Right here. And we're going to put a 5x cubed function in there as well. So it's 5x cubed, 5x squared, 3x, and 11, plus 11 right there. And then we're going to use this right here. And then we're going to plot it. And again, there's our function again. So all we do if we want to change polynomials is we just change x right there. Or change a. So it's a very easy way of plotting polynomials right there. So, okay. And that is going to be the end of what I want to talk about from this chapter. The only other thing I wanted to kind of spend a little bit of time on is absolutely necessary, and then I'll come back, and if we're out there, and we'll look at the book and try to go through some of the examples in the book that there is functions. And I'm not going to use the PowerPoint slides for functions. I just want to go through and give basically how to write a simple function right there. So I want to write a simple function that there, and let me just go back to here. And let's say that I want to write a function, and I want to plot the function, and I'm not going to use a polynomial, because if I have a polynomial, why not use polyval, right? I don't need to write a function. polyval is a function already written that there. Well, let's write a function that there, and I'm just going to make some arbitrary number. We're going to say that y is equal to x squared times sine 3x plus 2 right there. So that's a random function right there. I have no idea what it looks like, but we're going to plot this between -5 to 5 right there. And we may change that range once we see the plot that there. But I'm just going to go through the example of how I would plot a arbitrary function that there. And I don't care what function you can write, as long as you got a function that has one value here and one variable there, you can write a function to solve that there. So again, I like it so much better when I have two screens that have different things on them that there. I bet you I could do that here. Give me a second here. Oh, okay, hold on here. I'm recording, so it's going to have problems out there. Out there. Okay. Never mind what I was going to do. Let's go back to all right, my function is y equals x squared times sine 3x plus 2. Right, that there. Okay, so I'm going to come over here to right here, and I'm going to hit new function right there. Right there, new function, and I'm going to call this just simply F1 right there. We're going to receive in it X right there, and we're going to output F1 right there. Right there. Right there. Right there. And I think that's right. Give me a second here. Let me. I just wrote one to make sure it worked all right. That there. Right there. Yeah, we'll go with that. If I've got a mistake, then. Oh, ABC. Let me open up ABC. Okay, this is the format right here. ABC equals ABC. Okay, all right. That's the right there. ABC in bracket right there. So, oh, I closed that there. Let's start it again there. New function. Output argument F1 equals F1 right there. We're going to receive X coming into it. Here we're just going to simply say F1 is equal to, and our function was X squared. And I'm going to put parentheses around here just to make sure that it's clear. Times the sine of, what did we say, 3 times x, right there, plus 2, right there. And so there's our function definition right there. I've defined a function right there, and I'm just going to go ahead and save this, and we're going to call this F1. It's actually defaults to F1 because I named the function F1 right there. And down here, I could call F1 and pass it 3, for example. And the answer is 7.09 right I can say F1 20 through 20. And the answer is negative 129 there. F1 negative 5 right there. So I can calculate for any value for that there. But again, what I want to do is I want to plot this between negative 5 and 5, right? So I'm going to say x is equal to ln space, negative 5, comma 5, comma 200 points, right there. And space, right there. So I've created x right there. And then I just simply say y is equal to f1x, right there. And inputs must be scalar, and a square matrix. What do you mean that there? F1 line 2. F1 is equal to x squared times 3 x squared times 3 times x plus 2. Do I have a missing parentheses up there? Right there. Inputs must be scalar. Oh, me and this dot thing. Didn't I say that that dot thing would drive me crazy? Right there.
It has to be a dot, isn't it?
Yeah. And it's still giving me line 2 right there. Again, that's a scalar times. I shouldn't need the dot there. Dot times, I got that dot times here. Here using inner matrix must agree. Actually, that's a scalar right there. That's a single variable. All right, let's look at this. What's going on here? I don't see anything wrong with this, and all right, why is it?
Should be dot times C. Dot star C.
Dot star.
C.
Oh, okay. So in other words, you're saying I need the dot here as well. Right there. As I said, that dot drives me crazy. That time it worked. So you caught the right dot that was missing. That there. So it shouldn't need a dot here because that's a scalar, but this is a matrix and this is a matrix there, so it needs the dot there. Yep, you're right, that there. So then we just simply plot. Again, we're going to plot F1, or no. We y, yeah, we plot x and y, right? Yeah, we just plot x, y right there. I can't spell plot. Plot, P-L-O-T. That there, okay. So again, that there, and we can go through in here, we can exchange our range for minus 15 and plus 15. Right there. We use the one at there, and we can see that there. So we can plot any function that there. Again, hopefully you do it without, you know, at there. But the steps are fairly straightforward. If I could do it with a headache coming on, anybody can do it. At there. So the steps are fairly straightforward here. Let me just kind of go through here. This is where I define the function, and this is the function variable name right there, f1, and this is what we call our function. I keep the same name for both. This is what I pass the function. Now you can pass more than one item to the function right there. So I can put like a y, or put a k here, and here I can say plus k right there. Right there, and I can say times k right there. Right there. And now, when I call this function right here, I would pass it two values. One, that there. So when I call this function right there, and this gets a little tricky, right there, is that I'm going to pass it x, and then I got to pass it a value of k that's going to be fixed, for example, right there. So now when I plot this thing here, it's just going to be offset by a little bit that there. You know, I don't see where it's offset, but it does. It changes the function a little bit, because if someone can remember what it looks like there, and then you can see when I change k, I change the frequency of oscillation there. Again, when I change the frequency of oscillation, that goes from the fact that here, this is x squared times the sine of k times x. So when I increase k, I increase the frequency there. Actually, this plus k doesn't do anything right there. And because this is x squared, these frequencies goes up. Whether I go negative or positive. So this is an unstable system right there. But the key thing is we define our function, and to define a function, we just simply go here to new function, and it gives us the shell right there. And you can put in any function you want right there. This normally you can have multiple outputs from a function. I don't recommend it. I just think like C, you have one output. You can have multiple inputs to a function. I like to have just one output. That there. And this is on function title 4. You can I usually change that name to meet the output argument there. And usually one line of your function has to be ABC. The name of the function is equal to something on the right. That determines that there. You can also use the return and give it a value as well, but I usually just use the function name at there. I think, to be honest with everyone, at this point, I think I've covered all that I'm going to cover at there. We said about 3 o'clock or 3:30. I'm really to the point I'm wrapping up here at there. I wanted to make sure that I covered function.
Did you say example using the block diagram?
Yeah, well, that's the last thing I was going to do. I was going to wrap up with the slide, and I want to go through the book and just grab a couple of examples out there. So I'm going to leave MATLAB open right here, and I'm going to close this here, and I'm just going to open up the textbook right there.
It's not in the slide, huh?
I don't think it's in the slide right there. I think it's in the slide, but it's not very well. It's toward the end of the first chapter, as I recall. Let me find it real quick right there. Are you talking about this example here?
No, the one you show only the resistor block, this one, how to convert that one to formula.
Which one was that there? This was the one here where we were talking about it wasn't this one. I know it wasn't anything complicated like that there. I was thinking it was that one there, to be honest with you, that there, it was, no, that's the homework problem, not there. Yeah, it was that was the example. Let me just go back to that example and talk about that example that there. It was toward the end. It was right at the end of chapter 1 because I remember talking about this morning, right there. But the slides cover it, but the slides only give part of the discussion right there. It was this one right here. Okay. Right here. So what they're saying, the problem is that you work for a company that sells packaging for that there, and they develop a package, a type of package that will protect the object inside the package that there, as long as it hits the ground at less than 25 feet per second right there. So that's a key point right there, is that the package is good as long as your final velocity is 25 feet per second. So that's the key thing there. The package weight is 20 pounds, and its dimensions is 12 by 8. And your job is, will this provide enough protection if the delivery person comes? So understand the problem. And this is going through step by step. First thing is, the implication here is that the package is being protected. If it's dropped, it has to hit less than 25 feet per second. The assumptions are that you're not going to throw it up in the air. You're not going to throw it onto the ground. You're not going to drop it off the truck. It's only going to be dropped. And the reason you need to make that assumption is that you have to assume that my initial velocity is 0 feet per second, right there. So I'm going to drop this package from a height and I have to determine what height I can drop it from where the final velocity is equal to 25 feet per second. Unfortunately, this is an American textbook, and they use American units. I used to say English units, but the English all use the metric units now. So now I refer to them as the American units Although the English would probably still say that they're English units because they used them for a few hundred years before they switched over So again, the discussion here is the package is dropped from rest with no vertical or horizontal. It doesn't tumble or roll. All we do is drop it right there. The effect of air drag is we can ignore. We're only dropping it, the package is, 6 by 12 or something like that. I can't remember what the dimensions were of the package. Rectangular, 12 by 8. So it's not a round disc or something like that. It's a rectangular box right there. 12 inches by 12 inches by 8 inches. So it's going to drop with nominal air friction at there. So, and it's 20 pounds, so it's not super high density. So there's nothing magical about this package at there. So it's just going to drop. So it's going to use the normal drop from rest, the greatest height which we can drop it from. We're going to say is 6 foot tall. We're assuming that the person carrying it's not 8 feet tall at their normal height at there. So we look at this right here, and we've got some formulas right there. And our formulas are height is equal to 1 over g times t squared, and that's the initial time, your time at there. And VI is equal to GT. So these are some formulas that we've got from basic physics, auto mechanics, that there. And conservation of energy is their mass times gravity times the height is equal to mass times velocity squared, right there. Again, these are from basic physics. But there, I don't remember my basic physics because that was 35 years ago. That there, and I don't use these formulas very often, but I suspect the folks in the mechanical department do, right? These are very common equations for you that there. I mean, I remember seeing the formulas, it's just I don't use them very often that there. So, that there, this is our picture of what we're looking at. We have a velocity, we have a mass, and we have a height right there. Right there. Now our mass is given in pounds, so you would have to convert that to newtons if you're working in American or English units. Or you can convert everything over to kilograms, because that's a unit in mass there in terms of the metric unit, and you'd have to convert your feet to meters and your velocity to meters per second right there. So you have to pick what units you're going to work with at there. So our height is equal to V squared right there. Now again, this is the only formula we need in this case. And the reason this is the only formula we need in this case is because right there is because we're given the final velocity right there is going to be 25 feet per second right there. We're given our final velocity, we're given g, and we're looking for the height right there. So simple conservation, but we're given this particular formula right here. Right there, height is equal to v squared over g, right there. Right there. So this becomes 25 feet that there divided by 32 feet per second squared, right there. And this is what we would put in the MatLab in order to solve it. So this is a relatively straightforward one. The key to this example is not necessarily a MatLab example. This is a key in how you want to teach students how to solve the problem. That there is you get them to draw the picture, you get them to just write down what they know. You know, write down all the equations that they know, and then try to find a relationship. And the key thing here is we're making the assumption at the beginning, and this is where you will have problems, and I know that we will have problems out there, is right here, is when we look at this question right here, is that we didn't tell the students in this problem a maximum height right there. Now, what we did is we found out what height we can take this box to, and it would hit the ground at 25 feet per second. And by using these formulas, we determined that if we drop it from 9.7 feet right there, if we drop it from 9.7 feet, it's going to hit at 25 feet per second right there. So we determined the height we got to raise that to in order to drop it. Our problem definition told us that our final velocity, the protection level is 25 feet per second. That's our final velocity right there.
It's still intact.
They'll still stay intact. So getting the student to look at this problem and realizing that he's got all these formulas here, they have to pick which one is going to be the most relevant right there. So this one here is height right there. And what we're looking, the student is going to sit there and go, all right, I know the height. Does it tell me whether the box right there? So it's the thinking process is what's really this whole example.
Bottom line is we still have to think.
You still have to think that there.
MatLab is only the
Yeah,
tool.
MatLab is just a tool. You still have to look at the problem and say, what do I need to know? And what you need to know is you need to know the maximum height that this thing can be dropped from. And that's not said in the problem. The problem says right here, the problem right there says, right here, where is it here? That there. You are told that a new packing material can protect the package when dropped, providing the ground hits at less than 25 feet per second. Then it tells you the package weight, it tells you the dimensions. You don't need any of that information. Again, this problem is giving information that the student doesn't need. And students will spend half an hour trying to figure out where to put that 20 pounds in.
20 pounds we need, right?
No, you don't need it.
We need to-
You don't need that 20 pounds. You don't need the dimensions. The only thing the dimensions tell you is that it's a regular package, that there's nothing unusual about it. So that you can use normal physics equations right there. So there's nothing in this problem that you need the mass for, or you need the surface area, or any of that stuff. None of that is needed for this problem right there. So this particular problem is a typical problem that you would put on an exam or something like that there, where you want to see if the student can solve a problem, because you're giving them more information than they need, and you're not telling them exactly what they have to calculate. Now, you see, I consider this an example of a complex problem right there, because you're not telling the student what to solve for in the problem. The student has to sit back there and go, all right, how do I solve this problem? Right there. And they know, from physics and your courses, they know that they've got some equations here. They know that the height is equal to the final velocity squared divided by g, right there. That comes from basic physics. They also know that the height is equal to 1/2 v squared over g, right there. Again, do you need that? Right there. So given the calculations rounded off, we just use that first equation right there. Again, what we're looking for is we're given VI. Well, we don't call it VI. We just simply say that the student has to figure out, looking at this formula, that this package is only going to protect this up to 25 feet per second. So that's your final velocity when this thing hits the ground, right there. And then you determine how high can it be before it's going to, before the final velocity is going to exceed 25 feet per second. So if I solve for h here, then that gives me the height in which I can drop this package and it will hit at 25 feet per second. Anything higher, the final velocity is going to be greater than 25 feet per second. Anything less, the final velocity will be less than 25 feet per second. So again, but you're not telling the student that in this problem out there. You're just simply saying, I've got this package right here, and as long as it hits the ground at less than 25 feet per second, this package will survive. So is this package good enough for a delivery man, the post-logic guy, is this package good enough for him to carry this package around? Again, you would tell the students up front, now this, don't, make the assumption that the guy will only drop it. It's not going to fall off the back of the truck and roll around and get run over by another car. You're only worried about the person dropping it right there. So the assumption is it's only going to fall. You're not going to slam it in the ground. You're not going to throw it 20 feet up and then have it fall down. You're just going to fall. He's going to carry a stack of packages and it's going to fall off the top right there. So is this good enough? So this is what we got. Here's our package. It falls. It's at a height and it's going to hit the ground with that there. So our height is going to be right there. Again, we solved this. This is a problem here is, and they may not have the problem in this form. They may have the problem VI is equal to the square root of whatever. I mean, in other words, this problem that there. So they may have to solve for this particular problem right there. And again, this problem can be rewritten with, G being 9.8 meters per second squared, and you convert the final velocity to however meters per second that is right there. So 25 feet per that's going to be about, we'll say 3 meters per second right there. That's 9 feet that there. And 1 meter is roughly 3 feet, so 25 feet. So we're going to say about 8 meters per second. That there's your final velocity. So you can just reword this problem, convert it to metric units at there. But again, this is, I consider, now EAC may not consider this a complex problem. I think for a freshman student, this is a very tough problem. There's nothing difficult in the math for it right there. And then, of course, the calculation in MATLAB is basically just 3 lines right there. So, this is just one example. Now, again, this is not really a MATLAB instruction. This is kind of a type of problem that I consider complex that they would use MATLAB to solve right there. But this whole thing goes back to that whole discussion that I did earlier where I listed this table, 1.6.1, of the problem-solving process that there. So, and this is on what page? This is on page 52 of that textbook. And I look at this as a good example of coming up with some type of problem that again, this is for more of a freshman, sophomore type course, but you're not telling the student what they're looking for. You're giving them a hypothetical situation, and they have to figure out what they're looking for. They have to go through their repertoire of formulas and figure out how to figure out what they're looking for. And in this case, we're looking for this height that there, even though we don't say what height can we drop this from. We don't ask that there. We just say, is the package good enough? We made the assumption earlier that the delivery man was around 6 foot tall at maximum. So that should have been a hint right there. When we look at our assumption right here, right there, package is at rest right there. And again, we made some assumptions right there. Steps at there. And where's our assumptions? I remember reading through the assumptions at there. Delivery carrying is not detected at that there, make it at there. Collect known information at there. And Newton's laws, right there. And I remember reading it, and I'm not finding it.
What, the weight?
No, not the weight. The assumption where we said, assume that it's going to be around 6 feet is the maximum height that there.
Or indicate the height of the delivery man.
Yeah, the height of the delivery man. Because I remember reading it says,
Yes.
that we assume that there's no 8 foot delivery man.
Where? Page 53.
Page 53. Okay.
D.
Item D. Yeah, there we go. Yeah, see, these are the assumptions we made, and you missed it. I've been complaining about my head is starting to pound again on me that there. So that there. Actually, during lunch it's that there. So this afternoon's going to be short. That there. But again, as we go through here, and we made the assumption right here. D. This is the key. This is the key hint right there. The greatest height that tells the student what they should be looking for. it's buried in the problem out there, is that the height must be less than 6 feet or less. When they go through the calculations, they end up with a height of 9'6". So the answer to the question is the packaging is good enough out there. So, any other? Well, is this the example you were wanting me to go through out there? So it's a good.
Interestingly, the weight is irrelevant.
The weight is irrelevant. The dimensions are irrelevant. You know, when we look at this problem, there's so much information given that will completely confuse a student out there. That's what makes this problem complex is out there, and it's not uncommon for complex problems to give more information than is needed out there, because that forces a student to go through and pick out what information is relevant. That's part of the problem-solving process right there. So I'm going to stop at this point. I have nothing more to add. It's been a fairly interesting class. I hope